All right, so good morning, everybody. Last day of January, January the 31st. So January is just about over with. WebAssign homework. Your next WebAssign homework is due February the 4th, and I think it's just one section is due February the 4th. So pay attention to the due dates. The grace period for WebAssign is ending today. So I know that there's still a group of you who don't have the access code yet, and so you really need to be taking care of that, and so you can not get behind on your WebAssign homework. So please take care of purchasing the access code, getting yourself completely registered for WebAssign and everything. I have posted the solutions to the inequality problems, and I don't know if I sent them to you or not. I don't remember if I did or not. Did I send those to you?
I thought you said you posted it, but I haven't checked.
Yeah, I did post it. I know that. It's posted in the exam reviews. So this is, these inequality problems are in with the exam reviews, but I was thinking I had sent it to you also. I just could not remember if I had or not. The review is posted. Make sure that you use the downloaded version of the textbook when you are looking at problems on that review. The review has got both problems from the textbook and problems that I've added. I've got 14 or 15 of my own problems on there also. The solutions to all of my problems are part of the review. The answers to the textbook problems are in the back of the textbook. Also remember that you have to use the downloaded version. See, so look, you can, if you view the textbook online, if that's what you pick, then the page numbers, and there are no real problem numbers on there on that online version of the textbook, so that you can't use that version when you're looking at the review. Also, if you access the book through WebAssign, you're getting that same online version, and so none of the problem numbers are there, and I don't think there's page numbers there really either. So you do need to download a version of the textbook, and then you can use that downloaded version to find the problems that I'm telling you to look at on the review. So I just wanted to kind of point that out. The window for taking exam 1 opens a week from tomorrow, so February the 8th through the 13th. I will not make exceptions to that window. So be thinking about when you're going to take the test and where you're going to be taking the test. Cynthia.
Professor, can you tell me what sections exactly are covered on the exam?
Um, basically, basically, I would say it's 2.5, 2.6, and if we're looking at it by section number, it's 2.5, 2.6. The stuff on inequalities, which is not in your textbook,
Yeah. Mm-hmm.
and then
So
3.1, 3.2, and 3.3.
Okay. Okay.
3.5 is the next section we cover. Well, we will cover section 3.5 next Tuesday, but that will not be on your exam. So there's material. The exam will more or less end with what I'm covering today. We may go a little bit past that today, depending on how things are going. But the test will essentially end with what we do today. So. All right, any other questions anybody's got about that, about the exam?
I'm good.
No questions? Okay. Then let's see. I remember I will be on campus next week also, February the 7th and 8th. February the 7th from 4 to 6, February the 8th, 9 to 11. So now the 7th is a Wednesday. So next Wednesday, there will not be any lecture. Right? I don't lecture during that time period where the testing occurs and when I'm on campus. So I'll be on campus on February the 7th, a Wednesday. There will not be any live lecture that day. And then the following Monday, which I believe is February the 12th, also no live lecture that Monday as well, right? I don't live lecture during that exam period at all. So I wanted to make sure you understood that also. Finally, today we are going to continue on our discussion with functions. So we're going to look at function notation, and I know there's some function notation questions on WebAssign that I know have kind of confused some of you. I've gotten some questions through WebAssign on function notation, and we've only started getting into that, and so we'll get into that in a big way today. We'll also talk about difference quotients. We'll look at finding domains from equations. Last time we found domains and ranges from graphs of functions and relations also. Today we're going to look at equations of functions and talk about how you might go about looking at finding the domain for that particular function. And then finally we'll finish by starting our talking about graphing functions, some basic ideas behind graphing functions today, including plotting points and symmetry, talk about what an even and odd function is and how that relates to the way the graph looks. And then we will, if we have time, we'll look at piecewise defined functions also. The piecewise defined functions, if we do get to that today, that will not be on your exam next week. All right, so we are going to get started. We are talking, first of all, about function notation. Now, first of all, remember with function notation, when you write, for example, f of a is equal to b, whatever the function f is, when you write f of a is equal to b, remember that that a value is the domain value, and you're inputting that into the function, right? The function represents the rule, and then the rule does something with a, and what does it do? It takes it to the corresponding range value. B is the range value right here. Another way that you might see that written sometimes, like in a textbook, is you might see that A is the domain value. It's also called the input value sometimes. It's also called the value of the independent variable. You'll see independent variables used more and more. And then f of A represents the range value, or the output value, or the dependent variable, right? And you're saying that the y value depends on the x value, right? The x value is considered the independent variable. The y value is considered the dependent variable. So this is an x value right here, and this is a y value right here when you're writing f of a. And finally, you might see it written as an ordered pair, that a is the x value and f of a is the corresponding y value. Right? So all sorts of ways that you can write it out. So now if we're given a function, f of x equals 2x squared minus 3x plus 4, right? So we've named that function. Remember that f of x is just another name for y, and so you'll see this written also as y equals 2x squared minus 3x plus 4. Mean the same thing. Now, for a whole lot of reasons, it's really to our advantage to go ahead and use function notation. When we're talking about functions, using function notation makes our lives easier in a lot of ways. So we'll typically use function notation when we're talking about functions. All right, so now if I've got this function, f of x equals 2x squared minus 3x plus 4, or y equals 2x squared minus 3x plus 4, then to evaluate things like f of 3, right, and we've talked about this in our last lecture, that means that the domain value, the x value, is 3, and so every place we see an x, if we're going to try to find the y value there that goes with 3, we're simply substituting 3 in place of x, right? And so every place we see an x, we substitute 3. I like to use parentheses when I'm evaluating a function like this, and I would strongly recommend that you do that wherever you see an x, you put parentheses, and there's a lot of reasons why that makes sense to do. Now with 3, it's not a big deal, but I get in the habit of doing that for every value that I substitute into a function. It makes things go a lot easier. Then you just do the arithmetic here, right? So this is 2 times 9 minus 9 plus 4. So you have 18 minus 9, which is 9, plus 4, which is 13. Right? So we've got that f of 3 Oh, excuse me. F of,
Bless you.
thank you, thank you. Whew. So you get f of 3 is equal to 13, right? And so you also get the ordered pair 3, 13, right? That would be 3 different ways that you might write that kind of thing out. Some of you have some issues with negative numbers, and you're not paying attention when you substitute in negative numbers. So please watch for that. One reason why I use parentheses is when you're substituting in negative numbers, you really need to use parentheses when you do that. And so when you try to do it without parentheses, you're going to make a sign mistake. So you just got to be careful. So this would be
a different number.
I'm sorry?
I ended up getting a different number for f of 3.
Let's see. So that would be 2 times 3 squared minus 3 times 3 plus 4. So that's 2 times 9 minus 9 plus 4. So that's 18 minus 9. I think I'm right.
Okay, let me redo that.
Yeah, Charlotte, this time I think you made the mistake this time. Charlotte, you're usually right, but I think maybe this one time I'm correct. What are you getting?
I was getting 5 because I was doing 9 plus 4 is 13.
But see, when you do that, you're violating order of operations because that's negative 9 right there. Because remember, the sign goes with the term.
9 plus 4. Got it.
Yeah.
Thank you.
It's not a positive 9. It's a negative 9. So you got to be careful. So let's see. 2 times negative 6 squared minus 3 times negative 6 plus 4. So that'd be 2 times 36, right? That's positive 36 there. Plus 18, right? Because it's negative 3 times negative 6 plus 4. And so you get 72 plus 18 plus 4, or 94. I believe that's correct in that case. So you get that f of negative 6 is 94, where you get the ordered pair negative 6, 94, like that. All right, so now let's start moving. Let's look at some other types of problems here. So, and I know these are the kinds of things that cause some uneasiness when you were looking at WebAssign. So let's look at f of negative x in this problem. So f of negative x, you don't do anything different than I did on the first two. So every place you see an x, you substitute negative x. And this is going to come back to haunt us later on today also. So substituting in negative x. So what happens when you square negative 1x? Well, that gives you positive x squared. So that's just 2x squared. In other words, the first term doesn't change at all. The second term, however, does change because you have a negative 3 times a negative x is positive 3x, and then plus 4. And so our answer there would be 2x squared plus 3x plus 4. The first term did not change sign, but the second term did. Let's see. If we looked at negative f of x, I know that came up in some in WebAssign also. So all the negative sign in front of the f of x, notice the x there's nothing going on with the x. The negative sign is in front of the function. And so what's f of x equal to? Well, f of x is equal to 2x squared minus 3x plus 4. And what are we doing? We're sticking a negative sign in front of the function. And that's what that really means there is when you write negative f of x, it just says stick a negative sign in front of the function. Or in other words, multiply the function by negative 1. Right? And so if you wanted to look at that as a negative 1 up front, you could. And so what does that do to the function? It simply, when you multiply through by negative 1, it simply multiplies every term by negative 1. So you have negative 2x squared plus 3x minus 4. It changes every sign in the function like that. All right, let's say we had f of 3x. So f of 3x, every place you see an x, you'd substitute 3x in its place. And so this is a good example where using parentheses saves you a lot of heartache, right, in our function. So notice I put parentheses every place there's an x. And then what am I doing there is like I'm parachuting in 3x, in for x, right? 3x is getting dropped in place of x every place you see it. And so what do I get there? When you go through and do that arithmetic, well, you get 2 times 9x squared minus 9x plus 4. And so that would give me 18x squared minus 9x plus 4, like that. Excuse me. And then, you do as much algebraic simplification as you can, and there's not anything else you can do there besides square out the 3x and then multiply the negative 3 times the 3x. So you're finished with the expression. All right, so please shout out if you have a question about something as we're going through these, because we're going to continue on with function notation, and it's going to get a little bit messier as we go through this. So, all right, so the next situation. So I'm going to look now. We're going to leave that function, and I'm going to write down a series of functions here. So let's say I have f of x is equal to 3, g of x is equal to 2x minus, let me write that better. G of x is equal to 2x minus 1. Let's say I've got p of x is equal to x squared minus 3x plus 2. And finally, let's say m of x is equal to x plus 1 over x minus 3. All right, so I've given 4 functions there, and so we're going to look at some things about these 4 functions. So let's look at and this whole screen here is going to be just a bunch of examples related to function notation and these functions right here. All right, so if we have g of a plus b, so that tells me to go to the function g, and every place I see an x, I substitute a plus b. So notice what I'm doing is I'm writing down the function g. Now g was 2x minus 1, so I wrote 2 times open parentheses minus 1. And then in place of those open parentheses, I'm substituting in a plus b. Right? A plus b gets dropped in place of x in that function g. And then you just do the arithmetic from there. So this would be 2a plus 2b minus 1. And that would be all you could do there, right? There wouldn't be anything you could do to simplify that. So you'd be finished. Next example, let's say I'm looking at f of negative 10. Now this is incredibly easy, and this is among the most missed problems that I'll see on a test. So I've got f of x equals 3, and I'm asking you to evaluate f of negative 10. Now f of x equals negative 3. Notice there is no x in the definition for the function. This is called a constant function right here. And so a constant function means that the y value is always equal to 3, right? That you never get any answer besides 3. So f of negative 10, what's f of negative 10 equal to? Well, it's equal to 3. What's f of 6 equal to? It's equal to 3. What's f of a plus 3b equal to? It's equal to 3, right? F of x is a constant function, and because it's a constant function, it takes every domain value to the constant 3 in this case, right? And so, that's how you evaluate a constant function. There's nothing you don't substitute in for anything there. All right, very commonly missed on a test, believe it or not. Next problem, let's look at m of t squared, let's say, m of t squared. So m of t squared would say every place you see an x in the function m, you're going to substitute t squared. So here's my function m, and I'm going to put these open sets of parentheses again like that, where every place I see an x, right? And then I'm going to substitute in t squared every place I see an x. So t squared gets dropped in place of x. And in fact, there wouldn't be anything you could do with that. You could drop off the parentheses in this case, and you just get t squared plus 1 over t squared minus 3, and you'd be finished. Right? Pretty straightforward. All right. Please yell at me if you've got a question as we're going through these problems. All right, the next one I want to look at, let's look at m of 3x minus 7. M of 3x minus 7. So I go to my function m again. And every place I'm going to put parentheses wherever I have an x, like that. And I place in 3x minus 7 every place I see an x. Now, this is one where you could do some arithmetic. You got 3x minus 7 plus 1 over 3x minus 7 minus 3. And so you've got 3x minus 6 over 3x minus 10. And if you guys would just give me a second here. Okay. All right. So, Alondra, can you hear me? Okay, I can barely hear you. I think I heard you briefly there.
Yes, I can hear you.
Okay, great. Alondra, the only thing I'd ask, I think this is your first day with us, if I'm not mistaken.
First time live, yes.
Yeah, right. And so when you log in, and you sounds like you've done it successfully, just make sure you mute yourself. Once you've logged in, just hit the mute button. And then when you have a question, then you just unmute yourself and ask the question, right? And don't hesitate to stop me as we're going through something. And I have no problems with you stopping me. So, all right. So welcome. We're glad you're with us today, and hopefully you'll find attending live lecture is helpful. So. All right, I know on WebAssign, all of you have had problems like this. Like I have negative m of x, and m of x is this fraction. And remember what we talked about a few minutes ago is that negative sign just says stick a negative sign in front of the function, right? So here's my function x plus 1 over x minus 3, and I'm literally just sticking a negative sign in front of the function. Now that has caused people some trouble, because when you do that, what I'm getting a lot of people saying is that changes the signs on everything, and on the numerator and the denominator, and that's not necessarily true, or not necessarily true. It's not true at all. This negative sign in front of the function means that there's just a negative 1 as a factor in front of the function. And when you multiply a fraction by a constant like that, you're not multiplying the top and the bottom by that. You're just multiplying typically the numerator by that negative 1. It's just one part of the fraction, not both of them. So this is the negative of x plus 1 over x minus 3, like that, or negative x minus 1 over x minus 3. So if you notice, the signs changed in the numerator of that function, in that fraction there, but it did not change in the denominator. So, because you don't have two negative ones there, you only have one negative one. So you multiply it by either the numerator or the denominator. And it's usually the numerator. All right, so we're doing good. The next one I want to look at, let's look at this expression. Let's say we have g of 3/2 minus p of 6. I know you had a problem in WebAssign that was similar to this one right here. So what you're doing is you're separately evaluating g of 3/2 and p of 6. So g of 3/2 would be 2 times 3/2 minus 1. The 2's divide out there, and you get 3 minus 1, which is 2. P of 6 would be 6 squared minus 3 times 6 plus 2, or 36 minus 18 plus 2, or 20. So what do? You take those two answers that we just got. Here's g of 3/2 and here's p of 6, right? And you're substituting those into the expression that we've got. So g of 3/2 is 2 minus p of 6, which is 20. So you get 2 minus 20, or negative 18. Right? Here's the 2 right there, and here's the 20 right there. Okay, so do each one of those little pieces separately, and then you kind of go from there. So, all right. So I'm going to copy 2 of these functions, and I'm going to carry over to the next page. All right, so let's look at some more expressions here. So if we have, excuse me, p of x plus h, p of x plus h. So we would go to the function p, right? We'd use the parentheses we've been talking about. And every place we see an x, we'd substitute x plus h. So this is x plus h here, x plus h here, like that, right? Just dropping those in place of x. And so then that gives me x squared plus 2xh plus h squared. Now you got to be careful. X plus h squared, first of all, let me write this down off to the side, is not equal to x squared plus h squared. Remember, you can't use rules of exponents on an addition problem right there. And so that's not true that x plus h quantity squared is x squared plus h squared. Really common mistake I see students make. What is x plus h squared? It's x plus h times x plus h, right? And then you could use the FOIL method to multiply it out. And I think a lot of you know the pattern for squaring a binomial like that. And if you know the pattern, you could just write down the factorization or the multiplication problem just like I did right here. All right, then let's continue on with the arithmetic. This would be minus 3x minus 3h. You're distributing the negative 3 through, and then plus 2. No common terms there, no like terms, and so there's no other algebra you can do. That's the expression, believe it or not. All right, so you get this big kind of long, kind of gross-looking expression there. Next example. All right, so the next one is g of x plus h minus g of x, all divided by h. Oh my gosh. H is just some constant here. And this is, this kind of quantity, by the way, is called a difference quotient. This actually has a name. It's called the difference quotient. And the one thing that the difference quotient gives you, and you may see this referred to in WebAssign possibly, is it gives you the average rate of change for a function between two x values. Right, so if you see them referring to in the textbook possibly the average rate of change, you're talking about a difference quotient. So calculus students frequently start with average rates of change and then they go on and do something else with that. So calculus students work with difference quotients frequently, and this is a particular kind of difference quotient I've got written here, and this is one I would like you to be able to evaluate for a function. So g of, you've got like little pieces to this fraction right here. G of x plus h, when you evaluate that, that's 2 times x plus h minus 1. And then that's minus g of x, which is 2x minus 1, like that. And then that's all divided by h. Now let me color code that a little bit for you. Here's g of x plus h right here, and here's where I evaluated g of x plus h. Right, g was the function 2x minus 1, so what did I do? I took 2x minus 1, and every place I saw an x, I substituted x plus h. And then, here's g of x. And here's g of x right here. G of x is just 2x minus 1. So I'm just evaluating each of those two little pieces of the difference quotient separately, and then I'm subtracting them. Right? And then you do the arithmetic. So this is 2x plus 2h minus 1. Right? I multiplied through by 2. And then minus 2x plus 1. You're distributing this negative sign through right here. And then that would all be divided by h. And then with a polynomial expression like this, you'll always get lots of canceling in a difference quotient. And so notice here the 2x's add to give 0, and the 1's add to give 0. And so we are left with 2h divided by h. And notice in this case the h's divide out also. And you're just left with 2. Now, g of x equals 2x minus 1 was an example of a linear function. And with linear functions, when you evaluate a difference quotient, you always get a constant as an answer. So difference quotient is always equal to a constant for a linear function. All right, that will always be true. For other functions, it is not true. So let's look at our p of x up there. So p of x is x squared minus 3x plus 2. So let's look at p of x plus h minus p of x all divided by h. Right? Let's look at the difference quotient for the function p. So I don't do anything different. I evaluate p of x plus h. I evaluate p of x. I subtract them. So what's p of x plus h? I write down the function p. In every place I see an x, I substitute x plus h. And by the way, we did this at the top of the page already. So you have x plus h squared right there, minus 3 times x plus h plus 2. And then I subtract, please use parentheses here or you're going to mess up the sign, x squared minus 3x plus 2, like that. And this is all divided by h. And again, let me color code that a little bit here so that you can keep everything straight. So p of x plus h is right there. Here is p of x plus h. Right? I go to the function, and every place I see an x, I substitute in x plus h in its place. And then here is the function p of x. And what do? I substitute in what p of x is equal to right there. All right, so I just evaluate each of those little pieces separately. All right, then you go through and do all the arithmetic. And this, for a quadratic, this is going to be kind of an ugly expression. So you have x squared plus 2xh plus h squared. Remember, we talked about that at the top of the page. That's what x plus h quantity squared is. Minus 3x minus 3h plus 2, and then minus x squared. Remember, that's why I'm using parentheses here, is this changes all of the signs in this second piece right here, because you're distributing through a negative 1. So that's negative x squared plus 3x minus 2. And this is all divided by h, like that. And then remember what I told you is that you'll get a lot of canceling when you multiply everything out. And sure enough, you do. The x squares add to give 0, the 3x's add to give 0, and the 2's add to give 0. So a bunch of terms go away here, and you are left with, in the numerator, 2xh plus h squared minus 3h, and in the denominator, just left with an h. And then you go ahead and you could factor out the h out of the numerator. Right? There's my common factor of h. There's my h in the denominator. Those cancel out. And you're left with 2x plus h minus 3. Notice you're not left with a constant for this difference quotient. Right? For quadratics, you'll never have a constant answer. For linear functions, you have a constant answer. For quadratics, the difference quotient will never be constant. All right. Now we're going to look at one more difference quotient problem. Let's say that I've got the function f of x is equal to 6. It's a constant function, notice. Does somebody have a question? Okay. So notice this is a constant function, and so if I was going to evaluate my difference quotient, right, there's f of x plus h minus f of x over h. For this particular function, remember what I told you, that when you have a constant function, it doesn't matter what you evaluate it at, you always get 6 as the answer in this case. So f of x plus h is 6. F of x is 6. Right, so in our difference quotient here, f of x plus h is 6. F of x is 6. all divided by h. And so you get 0 divided by h, or 0. Right? If you want to do the color coding like we were doing on the last screen, this is what you've got. And this ends up being so simple, I think it causes people lots of trouble when they do that, right? For f of x plus h, we substituted 6. For f of x, we substituted 6. You end up with 0. The difference quotient is always 0 for a constant function. And remember that it kind of makes sense if you think about it, because I told you that the difference quotient, the one thing it would give you, we're not going to explore this very much at all, but one thing it gives you is what we call the average rate of change of a function. But a constant function is never changing, right? It's a constant function. So since it never changes, it makes sense that its difference quotient would always be equal to 0, like that. Okay. Whoops. So, all right, that finishes difference quotients. So the next thing we want to do is we want to look at domains of functions a little bit. So domains of functions. Now remember, we've already done this from graphs. I do want to mention this again. From graphs, when we were talking about the domain of a function, you know, we might have for example, a function that looks like this. This is actually a type of square root function. Let's say we have a function that looks like this graph right here. Right? Let's say that that's f. Well, the domain of f, right, what x values we're using for that function. Remember, we did talk about that for quite a bit of lecture on Monday's class. But remember, the idea here is that you are walking along the x-axis from left to right, and the idea is when and you're looking vertically up and you're looking vertically down, and the question is, when do you see the graph as you're walking along the x-axis? And in this problem, what do we do? In this graph, we see the x-axis starting here at -2, and then we see it for every x value after -2, greater than -2. Right? And so the domain for f, this is how we might write that. If we write it with a capital D and a subscript of f, in interval notation would be -2 to infinity, like that. Right? So that would be the domain for that function. We're not going to worry about ranges right now. We're just talking about domains. All right, and then another problem. There was a kind of graph that we would have seen, that we saw last time. Let's say that we have a function that it looks like this. And this is a graph, remember, that has what we call a vertical asymptote on the graph. And so this graph, I'm going to say, looks like this one right here. This will be a kind of graph we will encounter later in the semester. Right? So as you're walking along the x-axis here, notice the vertical asymptote for this function. This vertical line that the graph approaches but never gets to is at x equals 3. Let's call this function g. Okay? Then you've got this vertical line that the graph does not touch. Right? The graph gets infinitely close to that graph, to that vertical line, but it never actually gets to it. So as this person is walking along the x-axis here, and they're looking up and they're looking down, they see the graph. You've got arrows in both directions, to the left and to the right. So this person sees the graph over here and continues to see it until they get to 3. And then at 3, they don't see it anymore. And then after 3, they see it again. So the only place they don't see it is at 3. And so the domain for g in this case is everything but 3. Right? So it's all reals, in words, all reals except x equals 3. In interval notation, you'd write that -infinity to 3, parenthesis, and then union 3 to infinity, like that. Okay? So a little bit more about finding domains from graphs, and we'll talk more about that throughout the semester. But what we want to do now is turn our attention a little bit to looking at finding domains from equations. What if we were given the equation for a function, and how do we write down the domain? So we're going to look at three categories of functions. So we're going to look at polynomial functions, square root functions, functions that are defined as square roots, and finally, functions that are defined as fractions. So we're going to look at, and those are certainly not the only three categories of functions we're going to look at this semester. That's just the only three we're going to look at now, at this point of the semester. So a polynomial function looks like this. It's just f of x equals a polynomial, right? So f of x equals 3x minus 1 is an example of a polynomial function. G of x equals x squared minus 5x plus 8 is a polynomial function. H of x equals x cubed plus 2x squared minus 3x plus 6 is a polynomial function. Right? The first one's a first degree polynomial, the second one's a second degree, the third one's a third degree, and so on. X to the fourth minus 16. Those are all examples of polynomial functions. And the great thing is, with a polynomial, one characteristic of all polynomial functions, this is always true, the domain is always all reals for a polynomial function. They're always defined everywhere because it's just powers of x is all you're talking about, and multiplication and addition and subtraction. So the domain for a polynomial function is always going to be negative infinity to infinity. Nothing to do there. As soon as you identify it's a polynomial function, you simply write that its domain's all reals. Then you're done, right? If I ask you to find the domain, in other words, what x values work in the function that we're talking about, all x's, all real x's work for polynomial functions. It's always true. So, gee, that's easy, right? And will you have a problem like that on your first exam? Absolutely, yeah. You're gonna have a section where it's gonna say find the domains for these functions. One of them at least is going to be a polynomial, right? Nothing to do there. If you identify it's a polynomial, you can just write that its domain is automatically all reals, and you're done. All right, so let's look at the other two examples, square roots and fractions, and let's see what the issues are there. So let's look at square roots next. Functions that are defined as square roots, and what the issue is with a domain for a function like that. So we're going to start off with something that's pretty straightforward. F of x equals the square root of x minus 2. Now, if we're trying to write the domain or find the x values that work for this function, right? If we're trying to find the domain for this function, I want you to think about substituting some x values into this function for a minute. So like if you find f of 3 is no big deal to evaluate. You just get square root of 3 minus 2, which is the square root of 1, or 1, right? And you get the ordered pair 3, 1 on that graph. No big deal. F of 4 is not a problem. That's the square root of 4 minus 2, which is the square root of 2. And you could find a decimal for that if you wanted to, or you could just leave it as the square root of 2. And you can say that you've got the ordered pair 4 square root of 2. It's about 1.4. It's a little bit bigger than 1.4. So no big deal. F of 2 is not a big deal. The square root of 2 minus 2 is the square root of 0. Don't freak out. I see students frequently freaking out on the square root of 0. Square root of 0 is just 0. But f of 1 is an issue, because f of 1, you get the square root of 1 minus 2, or the square root of negative 1. And the square root of negative 1 is imaginary. It's I. And when we're talking about functions at this point, we are only talking about what we call real valued functions. And so we do not want functions to be equal to imaginary numbers. And so we say here that 1 is not in the domain of the function. 1 is not in the domain because this function does not take 1 to a real number. It takes it to an imaginary number. Why did it take it to an imaginary number? Because the number that you ended up with underneath the radical was negative. And so you do not want the number under the radical to be negative. Well, so that means you do want the number underneath the radical to be positive or 0. And so that's how you find the domain for this function, is you simply take the expression underneath the radical and you set it greater than or equal to 0. And you solve that inequality, and you end up with x is greater than or equal to 2. And you've got it. You've got the domain. It's all the x values greater than or equal to 2. On a number line, there would be 2. And so you'd put a solid dot on the 2, and you'd shade everything to the right. In interval notation, the domain would be written like this, that the domain of f is bracket 2 to infinity. Right? So for domains, the moral to the story here then is, if you're trying to find the domain of f of x equals the square root of Bob, right? If you've got the square root of Bob, the square root of anything, doesn't matter what it is underneath the radical, but then what's got to be true about Bob? Bob has to be greater than or equal to 0. So that's what you do automatically to find the domain of a square root function, is you take the expression underneath the square root and you set it greater than or equal to 0. And then you solve for x. Right, so it's a pretty straightforward in that, hey, if you've got a square root function, this is what you do to find the domain. Right, take the expression underneath, set it greater than or equal to 0. So let's say we have f of x is equal to the square root of 4 minus 5x. It's defined as the square root of something, right? The square root of an expression. So to find the domain for this function, in other words, the x values that quote unquote work in this function, you take 4 minus 5x and you automatically set it greater than or equal to 0. That's another example of a linear inequality. To solve that linear inequality, you subtract 4, you divide by -5, but be careful, you're dividing by -5, so you have to flip the order symbol, and you get x less than or equal to 4/5. On a number line, this would be 4/5 right here, maybe on the number line. So what are you doing? You're putting a solid dot on 4/5, and it's shading everything to the left of 4/5. And so the domain for this function f, domain for this function f would be -infinity to 4/5. It's all x values less than or equal to 4/5 work in this function. Anything greater than 4/5 is a problem, is not in the domain. Right? It would give you the square root of a negative number. Now, I'm not going to go crazy with this kind of problem, but I do want to mention that you could have the square root, for example, of a quadratic expression. And this is why we did quadratic inequalities last week, right? To find the domain, what do? You take the expression underneath the radical and you set it greater than or equal to 0. But the problem here is that this ends up being a quadratic inequality. And remember how you solve quadratic inequalities. It's not so straightforward. This is the kind of problems we were practicing last week, where you have to make up this little chart, right, of signs and analyze the signs of all these factors, and find the critical numbers and all that. And so that could happen, right? The critical numbers for this function are negative 1 and 3. Right? Those factors give you the critical numbers. And then remember, what you have to do is you have to analyze the signs of those factors in between the critical numbers. Remember, we did this last week. And you go through and you take test numbers out of these intervals. Right? We did a bunch of examples like this, and this is the problems where I gave you practice problems to do. And I posted the solutions to those practice problems on your Google site. So this could happen. And then, you substitute negative 2 in, you get 2 negatives. For 0, you get a negative and a positive. And for 4, you get 2 positives. And so you end up with a plus, a minus, and a plus when you multiply those. We are looking for, and we will always be looking for positives for this kind of problem, right? And so the positives occur less than negative 1 and greater than 3. So on a number line, here's your domain, because this is the solution to that inequality. And so the domain for this function f here is negative infinity to negative 1 bracket, and then union 3 to infinity. Right? So it's kind of a strange domain. The domain comes in 2 pieces, and it's everything less than or equal to negative 1 and everything greater than or equal to 3. By the way, if you wanted to know the graph for this function, if you look at the graph, when we write down the domain, this actually means something as far as the graph goes. It means you're only using x values less than negative 1 and greater than 3. And so this graph for this function ends up looking like this. It's got 2 pieces to it. It's got a piece like that and a piece like that. And if you think, and it stops literally here at negative 1, and then there's a gap where there is no graph, and then it starts up again at 3. And if you think about it, if you were walking along the x-axis, what would happen? You would see the graph, as a person was walking along the x-axis, they would see the graph over here until they got to negative 1, and then it would be a gap, and they wouldn't see the graph as they were looking vertically up and down. And then they'd start seeing the graph again here at 3. And then they'd see it forever after that because of the arrow there. And so when we write these domains down, it does mean something about the way the graph looks for the function. All right, so now I'm not going to go crazy with quadratics, but that's something that could happen for a square root function like that. If it's linear, that is not really an issue. If it's linear, then you just solve the linear inequality like I did up here at the top, and that's not as big a deal. All right. Next type of function we want to look at. Let's look at functions that are defined as fractions. F of x is equal to a fraction. And this all has to do with this idea. You cannot divide by 0, right? You cannot divide by 0, right? That's all about that idea. And so when you have a function that's defined as a fraction, right, like let's say f of x is equal to x plus 2 over x minus 3, then what do you not want? Well, you don't want x minus 3 to be equal to 0. You don't want the denominator to be 0. So the denominator cannot equal 0. We don't care about the numerator, remember, but we don't want that denominator to be equal to 0. So how do you find the domain for a function like this, right? If you've got f of x equals something up at the top up here, and we don't really care what the expression is up here, but it's over Bob, right? If you have Bob in the denominator like that, then what do? You actually set Bob equal to 0. You find where the denominator is equal to 0. You solve that equation, and then you throw out all solutions. Right, so in our problem right here, right, if this is how you find the domain here, so I'm going to write domain for, and then a function like this, function defined as a fraction. I'm going to put a box around this. Then in our problem right here, what would we do? We would take the denominator and we'd set it equal to 0. And then we'd solve that for x and get x equals 3. So 3 is a problem in this function. It's an x value that would give you division by 0 if you tried to evaluate it. And so what you have to do here is you have to throw out 3 from the domain. You kick it out of the domain. So in a number line, this is probably easiest to just look at it this way. Here's 3. You're going to throw 3 out of the domain, put an open circle in the 3, but everything else gets included. So everything else is in the domain. It's just the numbers that make the denominator equal to 0 that you're throwing out. And so that would be the domain for this function. So you have negative infinity to 3 parenthesis, and then union 3 to infinity. And that would be the domain for this function f. All right, so it's pretty straightforward in that you always do the same thing when you've got a function defined as a fraction. Take the denominator, focus totally on the denominator and see what makes the denominator equal to 0. So here's our function, f of x equals x plus 6 over x squared minus 5x plus 6. A function defined as a fraction. All right, so we factor the denominator, and the denominator factors x minus 2 times x minus 3. So you want to factor it. And then what do you do here? You take the denominator and you set it equal to 0. And you solve that equation. You get x minus 2 equals 0 and x minus 3 equals 0. You end up with 2 and 3 as solutions. And so what do? You throw these out. Notice we do not care about the x plus 6 in the numerator. The numerator, we don't care if it's 0 or not. We can divide 0 by something. You just can't divide by 0. So on a number line, you literally, you mark 2 and 3 on there, and what are you doing? You're literally just taking those two numbers and throwing them out. Those go away. And you are left with everything else, right? You shade everything else besides the numbers you're throwing out. Like that. And so that would be a picture of our domain. And so in interval notation here, the domain for f would be negative infinity to 2, parenthesis, and then union 2 to 3, and close those in parentheses, and then union 3 to infinity. Right? You end up with 3 pieces to a domain like this. Okay, so we've taken care of how to find domains for those 3 kinds of functions, for polynomials, square roots, and fractions. And so you'll have some problems on your test next week, and there are problems on the review where I'm asking you to look at domains for functions like this. All right, so now to finish class today, we are looking, we want to now move on to graphing functions. Moving on to graphing functions. Now the first thing I want to mention just for a few minutes here, we're not going to spend a lot of time with this directly, but you ought to be able to plot points to at least get some ideas on a graph. And so when I say plotting points, if you have a function like this, f of x is 2x minus 3, then you ought to be able to make a little t-table and substitute in x and find f of x and actually get some points to sketch the graph. That's all we're really talking about here. And a representative sample of x values might be like -2, -1, 0, 1, and 2. Plotting points is difficult to know in general what kind of points to pick, what kind of x values to pick. This is a linear function, so that's easy, but with more complicated functions, that may be a difficult question to answer as far as what x values do you pick that makes sense for the function. You'll just have to get better at that as you get more experience with doing this. Right, so we're looking at f of -2, f of -1, f of 0, f of 1, and f of 2. So I might literally do this on a test. I might give you a function and start a t-table and ask you to finish the t-table and plot or sketch the graph. Right, so f of -2 is 2 times -2 minus 3, or -7. Now I'm not going to go through all the arithmetic there because this is easy arithmetic. F of -1 would be -5. F of 0 would be -3. F of 1 would be -1, and f of 2 would be 1. You know, and you've got enough. You've got enough to make a decent sketch of the graph. Right? You have -2, -7, which is way down here. -1, -5, which is here. 0, -3, 1, -1, and 2, 1. Right? And you knew it was going to be linear because of the way the equation was written, and you get a graph that's a line. Right? That's our function f of x equals 2x minus 3. Pretty straightforward there. F of x equals x squared minus 4. Right, when you look at this function, you get f of x. Whoops, I'm sorry. You're making a t-table here. Right, so you have x values and f of x values, or y values. Again, maybe we'll use this representative sample. If after these points, if you don't think you have enough to sketch the graph, then you can plot more points. But f of -2 would be -2 squared minus 4, which would be 4 minus 4, which would be 0. F of -1 would be -1 squared minus 4, or 1 minus 4, or -3. F of 0 would be -4. F of 1 would be -3, and f of 2 would be 0 again. So when you make a sketch of that graph, right, let's see if we've got enough points that we think we know what the graph looks like. You've got -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. And so, yeah, it does look like we've got enough to make this sketch in that it looks like we've got a parabola here. And for a second-degree equation like this, that's what you end up with, is a parabola like that. All right, so plotting points, this is literally what you're doing, is just substituting in x values and picking a representative sample of x values and seeing if you've got enough of them to make a decent sketch of the graph. Now, for more complicated graphs, this will not work. You can't plot enough points to really make an accurate sketch of the graph, or at least it's incredibly inefficient to do it that way. So we're going to have to come up with other ways to deal with sketching graphs of functions. And that's what I'm going to finish the day with today, is one thing that that's helpful for sketching a graph, helpful to sketch a graph if you know the function is even or odd. Okay, and so we definitely need to know what that means when we talk about an even function or an odd function. So a function where this is true, a function where f of x and f of -x are the same thing, like this. If f of x and f of -x are equal to each other, this is an example of what we call an even function. And we're going to look at some examples here, what I'm talking about. And even functions always have graphs that are symmetric with respect to, that WRT right there just means with respect to the y-axis. An even function and symmetry with respect to the y-axis mean the same thing. And this condition makes is connected to those other two. All three of those things are really saying the same thing. And the problem I just sketched, f of x equals x squared minus 4, this graph has symmetry with respect to the y-axis. If you folded along the y-axis, you get a graph that is a mirror image around the y-axis. So let's actually sketch that graph again. So we knew from the last screen, right, we were talking about this function, f of x equals x squared minus 4. That graph looked like this. Had these points on the graph. And this graph has symmetry with respect to the y-axis. If you look at each point, what I want you to notice is that it has a mirror image point around the y-axis. Right? Let's see how all these points pair up around the y-axis. That means that this graph has symmetry with respect to the y-axis like that. So this graph has symmetry with respect to the y-axis. And so that means that this is an even function right here. And look what happens when you look at f of x and f of negative x. F of x in this function is x squared minus 4. And look at f of negative x, which we talked about how to evaluate that earlier in class today. That's negative x squared minus 4. Or, remember, what happens when you square a negative like that, you end up with a positive. And so notice you get the same thing. F of x and f of negative x end up being equal to each other. And that means that you've got an even function. And by the way, it's, you can see one reason why it's called an even function is look at the power on the x. It's even, right? That's kind of what we're talking about here. So for even functions, if we look at another example here, look at this function right here. F of x equals x to the 4th minus 3x squared plus 8. So is this function even? Is this an even function? Right, and so what we do is we look at f of x, and we look at f of negative x. So f of negative x, every place we see an x, we substitute negative x in its place. And what happens here, when you raise these negative x's to even powers, they all become positive. And so you end up with x to the 4th minus 3x squared plus 8. You end up with the original function back. And so the answer here would be, is this an even function? Yes, it is, because you end up with the same thing. And so that means the graph, if we were to sketch this graph, the graph is symmetric with respect to the y-axis. Probably, the graph probably looks something like this. I'm not 100% sure exactly what it looks like, but it quite likely looks something like that. And not a super duper graph, but you can see where that kind of graph would have symmetry with respect to the y-axis. All right, so that's an even function, right? That's what we started off with. All right, so now a function, and this is the last thing we're going to talk about today. If a function has this property that f of x is equal to the negative of f of negative x. In other words, if those two things are opposites of each other, so in other words, f of x and f of negative x are opposites. That's what it means there. Then you are talking about an odd function. Oops. So this condition right here, right, where f of x and f of negative x are opposites, you get an odd function. This type of graph has symmetry with respect to the origin. And so we need to look at a graph that has symmetry with respect to the origin. And so a graph that has symmetry with respect to the origin is like the, and actually let's just go to the next page here, is like the function f of x equals x cubed, the cube function. If you look at plotting points to make a sketch of that graph, first of all, if you use -2, -1, 0, 1, and 2, you get f of -2, which is -2 cubed, or -8. F of -1 is -1. F of 0 is 0. F of 1 is 1. And f of 2 is 8. And you get a graph that looks like this one right here. You have 0, 0, you have 1, 1, you have 2, 8. Way up here, you have -1, 1, and -2, -8, which is over here. And so you get a graph that looks like this one right here. It has kind of like a little bend to it around the origin, and then it continues up like this. This is a graph that has symmetry with respect to the origin. And notice with respect to the origin, what you're saying here is that if you looked at the, let's see here. Okay. If we looked at the first quadrant, I'm going to shade quadrant 1 here. If you look at this quadrant, and you rotated this quadrant around the origin, notice it matches up with this quadrant, right? Quadrant 1 and quadrant 3 match up with each other, right, as you rotate around. So you're literally rotating this quadrant around counterclockwise. And as you rotate it around counterclockwise and you pivot on the origin there, those two pieces match up. So this is symmetry with respect to the origin right here. And notice what happens if you look at f of x, which is x cubed, and f of negative x, well, that would be the negative x cubed. And when you cube a negative number, you end up with a negative. And so this is negative x cubed like that, the negative of x cubed. And notice these are opposites of each other. And so when you get functions that are opposites, you have an odd function and you have symmetry with respect to the origin. So a function like this one, and this will be the last example of the day, if you have f of x is equal to, let's say, x to the 5th plus 6x cubed, and maybe you don't know what the graph looks like of that. You probably would not know what the graph looks like for that function. But if you looked at f of negative x, every place you substitute, every place you see an x, you substitute negative x. And what happens there, you're taking negative numbers and raising them to odd powers. And when you do that, you end up with a negative number. So you end up with negative x to the 5th, the negative of x to the 5th. And then this next term, that negative that you get from the cube, ends up turning the sign, changing the sign of that term. And so you end up with x to the 5th minus 6x cubed. And you could factor out a -1 out of that. And notice what you're saying there is that, that's f of -x right there. And if you look at f of -x and f of x, what do you see? They are opposites of each other. F of x and f of -x are exact opposites of each other. And so this function is odd. And so that means its graph is symmetric with respect to the origin. And so, you get a graph, a typical kind of graph that's symmetric with respect to the origin. We just looked at x cubed a second ago. But, you might get functions like this one right here. A function like this one is an example of a function that is symmetric with respect to the origin. And you've noticed that the quadrants match up with each other, right? So the quadrant 1, this one, matches with quadrant 3. And if you rotate, you'll get those to coincide with each other. And then quadrant 2, this quadrant right here, matches up with quadrant 4, like that. And again, if you rotate, you can get them to pair up like that. So that's an example of symmetry with respect to the origin. All right, so these are not simple concepts. For those of you who are with me live right now, those who are watching recorded, the stuff that we're looking at is not simple stuff. It definitely requires some practice to go back and try to be able to deal with these ideas. So now what I'm going to do is I'm going to assign, now this homework that I'm about to write down includes homework from last time also. But on 3.1, 3.2, and 3.3 total, this is what you should be working on for these problems. So this is on page 176. Like I said, this includes problems from last time also. 27 through 59 odd. And then 69 and 70, 69, 71, and 75. Those would all be good practice problems out of section 3.1. And then 3.2. This is on page 193. Problems 7, 9, 11, 15, and 17. Those would all be good examples to look at. And then 27 through 37. Still not quite finished with 3.2. There's still a little bit left to do there. And then finally in section 3.3, which we have started now, problems, this is on page 206, problems 5, 7, and 9. And then so I guess at this point that's it for that section. Okay, so all right. So anybody have anything they need to ask me before we shut down for the day who are listening live right now?
I'm good.
I'm good.
I'm good.
Okay, so the words, okay, so first of all, I know you're going to watch the Super Bowl on Sunday, or at least some of you are going to. On Sunday, my office hours, my online office hours, I'm going to change those to accommodate people who want to watch the game and still want to talk to me. So I think what I'm going to do is I'm going to meet from, at this point I would say I'm going to meet from 12 to 1 p.m. So a little bit of a change on my Sunday office hours, and I'll say 12 to 1 p.m. And if I do change those, I'll send a remind message to everybody. So everybody have a great week, great rest of the week, and please let me know if you have any questions about something. I'd be happy to talk to you about